Hi folks, so this week we're going to concentrate on operations with vectors defined algebraically. So let's just recap what we mean by an algebraic vector. So here we see the vector u, where instead of it being defined by giving you a specific magnitude and then a direction using, say, north, south, east, or west, or comparing it to another vector, what we do is we think of this vector as being placed on the Cartesian plane, and the way we define it is by starting at 0, 0 and ending at a point, say the point AB. And then what we do is we call this vector the vector AB. Okay? Now, while we're defining it with it starting at 0, 0, remember that this vector can still move around and it's still considered the vector AB. So in this case here, if we assume that the scale is going up by 1, this would be the vector 5, 3. Even if I move it around here, it's still the vector 5, 3. All right, so let's recall some of the disadvantages of defining vectors this way is that I don't sort of see in the definition of the vector the magnitude or the direction, like we used to before with what we call geometric vectors. But hopefully the advantages of using this form of defining vectors will outweigh these disadvantages. Now, one of the advantages is that it makes defining vectors in 3D much easier. So in 3D, we do the same thing here where we're working with a 3D Cartesian coordinate system. So you have 3 axes instead of 2, and they're all mutually perpendicular. So x is perpendicular to y to z, and z to x. All right, and same thing, we define a vector starting from the origin 0, 0, 0 and ending at some point ABC, which instead of being an ordered pair is an ordered triple. So A in the x direction, B in the y direction, C in the z direction, and the vector again is defined starting at 0, 0, 0 and ending at that point. All right, now we have to keep in mind that this is the same notation as we would use for the point ABC, so we just have to look at what the context is. All right, so let's start to see how we can operate on vectors in this way. So we'll start with 2D. 3D would be a bit tough to show without having you right there in front of me, but I think you can imagine that it upgrades pretty nicely. So let's start with some vector defined on the Cartesian plane. Okay, so it could be any vector, but let's say this one here, it's our vector 5, 3. Well, one of the things we want to do is we want to define the opposite vector, so the vector that has the same magnitude but going in the other direction. Okay, so if this was in the past, east 30 degrees north, we know it would just be west 30 degrees south. That's how we define the opposite direction, and you just keep the same magnitude. Well, here, if I notice that this vector, which is defined by 0, 0 to the point 5, 3, now is just going to be defined when we look at the opposite as just going in the opposite direction in both x and y. So this is just going to be -5, -3. All right, so we see that defining the opposite vector is very easy. It's just about taking the x and y coordinates and changing their signs to the opposite sign. Okay, so let's now take a look at the idea of scalar multiplication. So say I take a vector v. Okay, so in this particular example, this looks to be the vector 3, 4. Okay, could be the vector 6, 8. All depends on the scale of my Cartesian axis here, Cartesian plane. So let's take a look at the vector 2 times v. And you can imagine something very similar for 3 times v or 4 times v. And what we notice here is that the x component of 2v is just 2 times the x component of the original vector v. So 3 and 3 is 6. Okay, here the y component is just twice the y component of the vector v. So 4 and then another 4. So you realize that scalar multiplication, again, very easy. It's just about multiplying the individual components by whatever the scalar multiple is. Okay, it would be similar if it was 3. Okay, so this is nice, but not really a big improvement on what we had before, because scalar multiplication, again, was pretty easy using geometric vectors. But this is where now we're going to see one of the big advantages here is that if I look at addition, Now remember what you had to do in the past if you wanted to add two vectors. So you'd place them tail to tail, you draw your resultant here. So you'd have your magnitude of v and u. You would have to figure out an angle inside this triangle, likely this one here. You would use cosine law in order to determine the magnitude of the vector, and then you'd use, sine or cosine law afterwards to help you determine the direction. Okay. Even if, so for those of you who studied physics last year and would have done this using components, still a fair bit of work. You'd have had to break it down into horizontal and vertical components, add each pair, and then convert it back to a single vector to get your final answer. So a fair bit of work, but let's see what happens here when we define these algebraically. Excuse me. Okay. Let's look at the x component of my resultant vector, and like those of you who did this with components, you realize it's just the x component of the first vector plus the x component of the second vector. So in this case here, if I look at vectors u and v, the x component of v is 3, the x component of u is 5, and what do I get when I add the two vectors together? 1, 2, 3, 4, 5, 6, 7, 8. So in other words, the x component is just the sum of the individual x components. And you can see similarly for the y components. Okay, what are the y components? Well, for v, it's 4. For u, it's 3. And what happens when I add the two vectors together? I see that the y component of the sum is just 4 plus 3 is 7. So the sum of 3, 4 and 5, 3 are just 8, 7. Okay? Practically no work at all. Okay, so in other words, we've turned adding vectors, okay, into an exercise in just adding numbers. In other words, adding the x components of the two vectors and the y components of the two vectors. And similarly, you would define subtraction as just adding the opposite. Okay, so this is where we're going to see the big gain here. Now, while in 2D, that might be somewhat impressive, it's certainly much, much better when we go to 3D. Okay, so if you want to add two vectors in 3D, now again, this is tough to see drawn on a two-dimensional surface. It would be much nicer to see it in person. But you can imagine here that what I would do is to find the x component of this vector, I would add the x components of the individual vectors to get the x component of the resultant. I add the y components, okay, and I add the z components to get the z component of the final vector. Okay, so what this does is it allows us to more easily add in 2 dimensions, but it gives us definitely a much, much easier way to determine these sums and differences in 3D. All right, so let's now start to look at some other things that we can do. Okay, since we're working on a Cartesian plane, we can designate locations as points. So whether it's a Cartesian plane, and you can see that this can generalize easily to 3D, okay, is what about the vector that joins 2 points? Now I know that, okay, oh, I guess this one's stuck here. I know that I want to define this vector as though it was starting from the origin, but can I determine what that would be looking directly at these 2 points that define the start and end of the vector? Well, what I can do here is I can easily see that, well, if I were to move this to 0, 0, I can just count 1, 2, 3, 4, 5. So the x component would be 5, and then the y component would just be 1. Now that's great in 2 dimensions when I've got a nice Cartesian plane. This would not be easy to see in 3D. So we want something that doesn't rely on having to look at the diagram. All right? So since I'm producing this vector a to b, I'd like to work with vectors, and let's see how we can operate on them. And what we're going to do here is, instead of considering the point 3, 4, let's consider the vector 3, 4. Okay, and instead of the point 8, 5, let's think of the vector 8, 5, meaning from 0, 0 to the point 8, 5. And then all of a sudden we realize that this vector A to B joins the tips of two vectors that are placed tail to tail. And this is where we remember from back what we did earlier on, that when I have two vectors placed tail to tail, the vector that joins their tips is a subtraction. Okay? Now, if I'm starting at A and going to B, remember that it goes from the tip of the second to the tip of the first. So this must mean that this vector AB can just be gotten by subtracting OB minus OA. So in other words, 8, 5 minus 3, 4. All right? Which would give you the exact same answers we got before, because 8 minus 3 is 5. There's our x component. And then 5 minus 4 is 1. There's our y component. And what's nice about this setup here is it would work perfectly in 3D if this was in 3 space with an extra axis. All right? So what we have so far is our definition of algebraic vectors in 2D and 3D. We now have easy ways of adding them. It's just about adding or subtracting the individual components. And we have an easy way to represent the vector from one point to another. It's just subtracting the vector to the second minus the vector to the first. All right? There's one last thing we're going to take a look at in this video. Okay, and it's something that we're not going to spend too much time on now because its importance is really going to come later on, but it certainly will be an important concept for us later on. Okay, and it's this idea of, instead of writing this vector as 5, 3, there's an alternative. Okay, and it really is about indicating that this vector can be made up of a horizontal component and a vertical component. And so what we do is we define these two vectors, okay? And we call them I and j. Now here, I just used, bolded I and j, but normally you'd see me write them with I hat and j hat. And hopefully you'll realize why I would use the hat, because these are vectors of magnitude 1. So they are unit vectors, all right? So what I want to do is I want to produce this vector, which again is the vector 5, 3. So if I want to use these unit vectors to define that, I realize that I just have to take this unit vector I and multiply it by 5. That's going to give me the x component of the vector. And then if I want the y component to be 3, I just take this vector j and multiply it by 3. Okay? And so what I can do is I can write the vector u as 5i plus 3j. And we see it here if I draw them tip to tail. Okay, so this is an alternative way of describing these algebraic vectors as what we call, and this is an important term, what we call a linear combination of the vectors I and j. So what does a linear combination mean? Well, it means you can multiply the vectors by some constant, and then you can add and subtract them. So this would be a linear combination of the vectors I and j. If I were to write 5x plus 3y, we'd call that a linear combination of variables x and y. Okay, and this is all very nice, but this is actually not what's going to end up being important for us. Okay. So we call these two vectors, I and j, we call them the standard basis vectors. Okay, so basis vectors are vectors you can use by taking linear combinations and writing a new vector. Okay, and we call them the standard basis vectors because they're the easiest ones to use. So magnitude 1, and in the y direction, the x direction. All right, but this is the biggie here, is that these are not the only two basis vectors. In fact, you can use almost any vectors as basis vectors. So let me take this vector here and this vector there. And the question is can I take a linear combination of these two vectors to write vector u? Okay, so is there a way to do that? So somewhere here, I've got a hidden diagram, which we'll try to hit if I can find it. I promise it's hidden here somewhere. There we go. Okay, I guess it's being held up there. So let me see if I can draw it myself. All right. So what I want to do is I want to take linear combinations of those vectors. All right. So let's take this here. So if I notice here, if I take a vector, this blue vector down here, and I take exactly 1 times that vector, and then what I'm going to do is I'm going to take half of this second vector, and look what I can do. Okay, let's just test that out here. If I take this vector here, we see that it's exactly half this other blue vector. So what I can do is if I call this, say, vector P, okay, and then I take 1/2 of vector Q, (0.5) of vector Q. Okay, let's see what we have here. I take vector P plus 1/2 of vector Q. Look what I get. I get that same vector U. So I'm able to write U not only as a linear combination of vectors I and j, I can write it as a linear combination of vectors P and Q. All right? And in fact, I can do this with almost any pair of vectors in 2D. Okay? But there are some restrictions. Okay? So let's forget this one here. Let's say we don't use that vector, but use vector P. I think it's pretty clear that the other vector can't be the 0 vector because, even if I add 3 times the 0 vector, 4 times the 0 vector, I'm just adding P plus the 0 vector. It doesn't take me anywhere. Try to think, what other type of vector can I not use to guarantee that I can describe any other vector in 2D? Okay, so as I'm preparing for it, see if you can think of what other vector I shouldn't be taking. Okay, well, what if I take a vector that's parallel to vector P? Can you see that if I try to add linear combinations of vector P and say this is vector R, well, if I add P and R, what do? I just get another vector in that same direction. What if I add P plus 2R? I get just a vector in that direction. What if I add P plus negative 2R? You see that I'm only ever going to end up with vectors in that direction. Okay, so the other restriction on what we can use as basis vectors is I can use any 2 vectors as long as they're not equal to 0, either of them, and as long as they're not parallel. Okay, and we're going to see that this is going to be an important tool for us later on, that you can write any vector in R2 as the linear combination of 2 other vectors. And as long as they're not parallel, as long as they're not 0, that's enough. All right, so let's take a quick look at the notes here to recall. So here we have these standard basis vectors, I and j. Okay, so in 2D, they would be 1, 0 for I and 0, 1 for j. You can also do this in 3D, but we're going to end up needing it in 2D more than anything. But just to, just to let you know that you can also do this in 3D, that you can identify vectors I, which is 1, 0, 0, so in the x direction, 0, 1, 0 in the y direction, and 0, 0, 1 in the z direction. And you can write any vector as a linear combination of these three basis vectors. So I and j, or I, j, and k in 3D are what we call the standard basis vectors. All right? So we'll get to a more general thing later on. So here we have now our operations on algebraic vectors. Okay, so I'm going to focus more on the traditional way of writing out algebraic vectors. You can also use the standard basis vectors, but that's not going to be my what I'm going to focus on. So here, if I want to add two vectors, whether in 2D or 3D, all I have to do is add the individual components. So x1 plus x2, and then the y component, y1 plus y2. Okay. Similarly here, say I'm doing subtraction in 3D. I take my two vectors, okay, and if I want to subtract them, I subtract the x components, the y components, and the z components. Okay, take something like scalar multiplication. If I'm multiplying a vector by some scalar k, I just have to multiply the individual components by k. If I'm taking the opposite of a vector, I just have to multiply the individual components by -1. All right? Now, we also talked about how we can define a vector joining 2 points, whether in 2D or in 3D, and it's all about subtracting the second minus the first. Okay? The second minus the first, because we saw it as a subtraction of two vectors. All right? Now, we're not going to go through the proofs here, but defining vectors in this algebraic way makes proving these things, which we drew pictures of, much easier, okay, than if we were working with geometric vectors. So essentially, all those things that we determined, that vectors are commutative under addition, associative under addition, meaning it doesn't matter which ones I add first, and distributive under scalar multiplication, so I can distribute a scalar multiple to the sum of two vectors. Those all hold in 2D, and they also hold in 3D. So that tells us that we can use our knowledge of operating with numbers to help us operate with vectors, because we notice that the way in which we operate with vectors now is to work with the individual components, which are real numbers. And the last thing we're going to say here is that any two vectors can be basis vectors, okay? Meaning that I could take my vector xy and write it as a linear combination of these two vectors. There are some restrictions, though, is that the vectors, neither of them can be 0, and they cannot be parallel. But any other pair of vectors can be used to write a vector in 2D. Okay, there's also a rule for 3D, but like I said, our focus is going to be on 2D later on. That's it for this video. We're going to do some examples in the next one.